Alright, so now we begin a new chapter in this course, and that is to deal with differentiation, right? And in the context of differentiation, now we come back to functions that map R to R. So these are real valued functions on the real line, right? So before we define the derivative, let me quickly recall the definition of continuity here. So we say that a function f is continuous at, let's say, a, which lies in the domain of f, if the following condition is satisfied. If limit x tends to a, f of x equals f of a, right? And recall that the object that's on the left hand side of this equality, we gave a definition of this, both an epsilon delta definition as well as a sequential definition, right? So we have defined this object well already. If the limit of this as x goes to a of f of x matches the function value at a, we say that the function is continuous at a. All right. So now we can talk about what it means for a function to be differentiable at a. We say that f is differentiable at a if the following limit as x tends to a of f of x minus f of a upon x minus a. Okay, so if this limit exists and is finite, then we say that the function is differentiable at a. Okay, and when this limit exists and is finite, we call that limit to be the derivative of f at a. So we denote when it exists and is finite as f prime a, also called the derivative of f at a. Alright, so that's your definition of the derivative. This is something that everybody is already familiar with, I'm sure. So this is largely a recap. So if as x tends to a, the limit of this function, which is f of x minus f of a upon x minus a, if that limit exists and is finite, then we say that the function is differentiable at a, and the value of the limit is what we call the derivative of f at a, also denoted by f prime a. Okay, and one thing that I would like to point out that is implicit in both the above definitions is that f has to be well defined in some neighborhood around a, right? Otherwise these limits wouldn't be well defined in the first place. So implicit here is that f is well defined in some neighborhood around a. So one could equivalently say that f is well defined in some open set containing a. Right? Okay, so now that the definition is out of the way, we can do a few quick examples. So the first example we will consider is g of x is equal to square root of x for x greater than or equal to a. Sorry, x greater than or equal to 0. Okay, so this is a function over the non-negative reals, which is defined as simply the square root of the argument. Okay, now for a greater than 0, let's look at g prime a. Okay, g prime a, if it exists, is basically going to be the limit as x tends to a of, well, square root x minus square root a upon x minus a, right? But we know that this ratio is essentially the same as 1 by square root x plus square root a, right? So I can just use that representation to conclude that this limit does indeed exist, right? Because after all, we know that square root x is in fact continuous, right? So as x tends to a, square root x converges to tends to square root a, and so indeed you would get this limit to be 1 by 2 times square root a, okay? Which we all know to indeed be the derivative of this function at a. Okay. Next example, along very similar lines, you can look at g of x equals, let's say, x raised to n for, let's say, natural n. Okay, in this case, an elementary application of the same technique would tell you that the derivative is n times a raised to n minus 1, right? In other words, limit as x tends to a of x raised to n minus a raised to n upon x minus a. Again, this ratio can be written, right, because we all understand a factorization of the numerator in this case, and that using that factorization you will see quite easily that this limit is in fact n times a raised to n minus 1. Okay. So that is the definition of the derivative. What we are going to do in the remainder of this video is go through some elementary consequences of this definition, right, which will let us essentially apply, be able to differentiate a large wide variety of functions. Okay, so the first, shall we say, result is to say that if the function is differentiable at a, it is also in fact continuous at a, right? So differentiability implies continuity. If f is differentiable at a, then f is continuous at a. Okay. So differentiability is a stronger criteria than continuity. So the proof is fairly elementary. What we have to do is argue that suppose you have differentiability, then indeed as x tends to a, f of x tends to f of a. Okay. So I am just going to rewrite f of x as follows. F of x is going to be x minus a times f of x minus f of a upon x minus a. Right? This kind of representation is perfectly valid for x not equal to a. But remember, yeah, so plus f of a, right? So in particular, this is true for x not equal to a, because I'm, in some sense, multiplying and dividing by x minus a. But that's all right, right? Because to evaluate the limit of the function as x tends to a, I never need to actually evaluate the function at a. So it's perfectly fine to use this representation of f of x, which is valid for x not equal to a. Okay. Now from this representation, if I take the limit as x tends to a, well, the answer essentially follows. So in other words, limit x tends to a f of x is equal to, well, the limit of x minus a as x tends to a is 0. The limit of this square bracketed quantity is, of course, by definition, the derivative of f at a, and then of course we have the constant f of a, right? So overall this limit ends up being f of a, which is what we wanted, right? So this shows that if the function is differentiable at any point, it is also continuous at that point. Okay. The next theorem will basically collect some other simple properties about how derivatives combine. So suppose that f and g are differentiable at a. Okay, then the functions c times f, here c is some scalar, right? F plus g, the sum of the functions f and g, the product fg are differentiable. Okay. Additionally, suppose I assume that g of a is not equal to 0, then the ratio function f by g is also differentiable at a. Right? And finally, we know that if you look at the derivative of the function which is defined by multiplying f with the scalar c, the derivative of that at a is simply c times f prime a. Right? Similarly, f plus g, the derivative of this function at a is in fact simply f prime a plus g prime a. So the derivative is linear, so to speak. Right? If you look at the product, the derivative of the product at a, again this is something that we all understand, this is the product rule, this is just f of a times g prime a plus g of a times f prime a. Right? And finally, if you look at the quotient rule, this is called the quotient rule. This is the derivative of f by g at a, and of course we are only talking about this when g of a is not equal to 0, right, as written above. In this case, the derivative of f by g at a is given by g of a times f prime a minus f of a times g prime a divided by the square of g at a. Okay, so this is basically just how derivatives behave when you add differentiable functions, multiply them, divide them, or for that matter multiply them with a scalar. Okay, so the proof is fairly straightforward. So what I will do is particularly for multiplying the function with the scalar and adding two functions, I'm going to leave that as an exercise. That's a fairly easy exercise. So let's say 1 and 2 above are easy. So that's essentially left as an exercise for you. Let's look at the derivative of the product. Okay, to understand the derivative of the product, I basically have to look at the function f of x times g of x minus f of a times g of a upon x minus a. Right? The limit of this as x tends to a is indeed the derivative of the product function f of x times g of x. Okay. Now all we are going to do is rewrite this as follows. This is going to be f of x times, well, g of x minus g of a plus, well, g of a times f of x minus f of a upon x minus a. Right? All you have done is added and subtracted one term corresponding to f of x times g of a in the numerator, right? And that lets us split the original expression as follows. And now it's easy to apply the limit. As x tends to a, well, f of x tends to f of a because f is differentiable and therefore continuous, right? The second square bracket converges, of course, it converges to g prime a, and then this last square bracket in the second term converges to f prime a, right? So applying these, you would in fact conclude that as x tends to a, sorry, I should simplify that better. This means that as x tends to a, this goes to f of a g prime a plus g of a f prime a, right? And that is exactly what we wanted to show. So that's part 3. Let's move on to part 4, which is the ratio, right? Now again, to evaluate the derivative of the ratio, I have to look at the limit of the following function as x tends to a. So I have to look at f of x by g of x minus f of a by g of a upon x minus a. Okay, so this is also straightforward. Now all we will do again is to do some massaging of the numerator to show that the numerator is in fact g of a times f of x minus f of a minus f of a times g of x minus g of a, right? This whole thing divided by g of x, g of a times x minus a, right? All we have done is cross multiplied out the numerator of the fraction on the left hand side and then added and subtracted the term corresponding to g of a times f of a, right? So g of a times f of a has been added and subtracted to basically write it as follows. And now you can easily again see that since f of x minus f of a upon x minus a tends to f prime, as x tends to a, you have g of a times, well, f of x minus f of a by x minus a tends to f prime a, because f is differentiable at a. Similarly, you get minus f of a times g of x minus g of a by x minus a becomes g prime a upon, well, g of x. G of x of course tends to g of a because of the continuity of g at a, and so that gives you g square a in the denominator, right? So this is how you would prove the quotient rule. All really an elementary application of the definition of the derivative, right? As a easy application of this last rule, note that for m, which is again a natural number, let f of x is equal to x raised to minus m, right? And this is of course well defined for all x not equal to 0. Okay, so in this case, for a not equal to 0, you can apply this last ratio rule that we just did to argue easily that f prime a must therefore be minus m times x raised to minus m plus 1, right? So this is a trivial application of the last rule that we have talked about, right? So this basically covers the derivatives of